Hey everyone, welcome into lecture number 12 of differential equations. This lecture is on the method of undetermined coefficients. So let's start this lecture with a motivational example. Let's consider the second order linear differential equation. Consider the second order linear differential equation. This one's going to have constant coefficients, and it's going to be given by y double prime minus 3y prime minus 4y equals 3e to the 2t. So again, this has constant coefficients. It's linear, second order, so it's everything that we've been studying in this chapter. But the right-hand side is not zero, so this is not a homogeneous equation. This is what you might call a non-homogeneous equation. So the question is, can we solve this, right? Can we solve an equation for which the right-hand side is not the zero function? And the answer is yes, we can. Well, we can attempt to at least, right? And so our method is going to be to make a guess, because the right-hand side of this equation has a very nice form, right? So this method of undetermined coefficients is going to be exactly what it sounds like, which is we're going to make a guess, and we're going to then determine, based on our guess, we're going to determine the appropriate coefficient of our function to get the answer. So the method is to essentially make a guess. Make a guess, and again, because of the form of this right hand side, our guess is going to be, we're going to call our guess capital Y. So capital Y of t is going to be, we're going to guess that this is going to be some constant a times the function e to the 2t, because we know that as we take derivatives of e to the 2t, we're going to get back something times e to the 2t, right? And so that's all got to combine so that we're left with a 3 at the end, if this is the correct solution. So let's check it then. If this is really going to be a solution of this differential equation, then what do we have to do? Well, we have to take the derivatives and plug into the equation, right? So I'm going to rewrite everything here. So our y is going to be a, by the way, over here, let's write this. A is a constant, right? It's a real number that we're going to determine as part of our solution here. So capital Y is just going to be a e to the 2t. Then we need to take derivatives. So the first derivative is 2a e to the 2t, and the second derivative is then going to be 4a e to the 2t. And now once we have these, we want to plug these into the equation, right? So then we just plug them in, and then we'll be able to determine, hopefully, a value for a. As we plug these in, I'm going to write it symbolically first. Y double prime minus 3 times y prime minus 4 times y. Now we plug these in, right? So this is going to be 4a e to the 2t minus 3 times y prime, so that's 2a e to the 2t, and then minus 4a e to the 2t. And this whole thing, if we combine all these like terms, right, everything has an a e to the 2t. We have 4 minus 4, those are gone, and then we're left with negative 6 of them, right? So negative 6a e to the 2t. But this is supposed to equal, from our differential equation, this is supposed to equal 3e to the 2t. So that's what's got to go here, right? And so this will be 3e to the 2t. And then we notice that we have an equation now where we can solve for this coefficient a, because we have e to the 2t on both sides. It's not at 0, it's a positive function, right? Those cancel, and so now we're left with, okay, this equation here says a has to be negative 1/2 for negative 6 times a to equal 3. So there we go. We have determined the coefficient, right? And what we found then is that what we're going to call our non-homogeneous solution. So non-homogeneous solution, which is capital Y, right, is capital Y. We reserve this capital Y for our non-homogeneous solution. So capital Y is negative 1/2 e to the 2t. So this is the part of our solution. Notice I'm saying part of our solution for which, when we take the derivatives and we plug in, we get back the right-hand side, the non-zero function on the right-hand side. All right? But there's going to be more to the solution, and I've already alluded to that by saying this was only part of our solution. What's going to be left over? Well, you're allowed to add 0 to anything, right? You can always add 0 to a number, or a function in this case, without changing it. So what we have to do then is take our non-homogeneous solution, the part that gives us this, and add to it our homogeneous solution. So this is what we've been studying in the previous lectures, right? The homogeneous solution is going to be the solution of this differential equation that gives us a 0 on the right-hand side. So to get our complete solution, we now need to find the homogeneous solution. And in reality, I've done this in the wrong order. We should always do this first. And we'll see why a little later in this lecture, but we should find the homogeneous solution first. But now for the homogeneous part. So this is going to be, we're going to call this part of our solution y sub h for the homogeneous solution. And we know how to solve this one, right? So this is this differential equation, the homogeneous equation, the corresponding homogeneous equation, is y double prime minus 3y prime minus 4y equals 0, right? And this has characteristic equation r squared minus 3r minus 4 equals 0, and this one factors, right? So this is going to be r minus 4 times r plus 1. And so the two solutions, two linearly independent solutions of the homogeneous equation are going to come from these values of r, right? So r is equal to 4 and r is equal to minus 1. So this then tells us that our homogeneous solution is c1 e to the 4t plus c2 e to the minus t. And of course those can be switched. The c1 and c2 are unknown constants, right? They're as opposed to undetermined, they are unknown constants. They're free, right? They're free variables. All right, so now what we end up with then is that the general solution of this differential equation has to include both parts. It has to have the homogeneous part and the non-homogeneous part. All right, so the general solution of the DE, which I'll rewrite, is y double prime minus 3y prime minus 4y equals 3e to the 2t, non-homogeneous, right? This is given by, so the solution itself is y. It's given by capital Y, non-homogeneous part, plus y sub h, homogeneous part. And we've determined both of those, so we can just write down the solution then. It's going to be negative 1/2 e to the 2t plus constant 1, c1, e to the 4t plus unknown constant 2, e to the minus t. And we need all of this, right, to write down our general solution. Okay, so that's a motivational example. We started with the non-homogeneous equation. We made a guess. We worked out what the coefficient must be. So the guess included this coefficient a. We worked out exactly what that coefficient must be to be a solution. And then we noticed that we can always add 0, right? And so therefore we have to add the homogeneous solution as part of our general solution. And that's it. That's the method of undetermined coefficients. Now, what's going to make this more complicated or more difficult is different right-hand sides, right? So if it's really hard to guess the function that's going to give you the right-hand side after plugging into the left-hand side, then this method doesn't work that great, right? So let's look at a couple more options for right-hand sides that are going to be like good for us to guess, good candidates for us to try to make a guess. So let's stick with the same left-hand side. So the same left-hand side, y double prime minus 3y prime minus 4y. But this time let's change the right-hand side to 2 times sine of t. And now we want to try to solve this. So we already know that our homogeneous solution is going to be the same, right? When the right-hand side is 0, this is the same homogeneous equation that we had before. So we'll stick with this, right? So it's c1 e to the 4t plus c2 e to the minus t. But this is going to have a different homogeneous part because non-homogeneous part, because the right-hand side is different, right? It's different. So in this case, we need to make a guess of a function for which when we add together its linear combinations of its second derivative, its first derivative, and itself gives us back a sine function. Well, since itself is 2 times sine, right? But since itself is on the left-hand side, we need to imagine that there could be a sine of t component. But since the derivative is involved, there has to also be the option, the possibility, that a cosine of t is going to be involved, right, in our guess, because the derivative of sine is cosine. And then finally over here, y double prime, that's going to be another sine. It's going to be minus sine, right? So the guess when we have a trig function here is going to be the following. So y of t, capital Y, is going to be a times sine of t plus another different constant b times cosine of t. So we have to make sure that our guess includes both sine and cosine, because both of those could give us sines right here, right? Derivative of cosine is y prime, right? Would be sine, sorry. Derivative of cosine would be a sine, so at this point it could give us a sine for the right-hand side. All right, so the method though is the same. Now we take the derivatives, we plug them in, and we try to determine our coefficients. So I'm going to give you guys a few moments here to work on this one, and I'll check back in with you to see how you did. All right, let's see how it went. We have to now take the derivatives before we do anything else, right? So y prime of t, derivative of sine is cosine, so this is a cosine of t minus derivative of sine is negative, derivative of cosine is negative sine, right? So minus b times sine of t. And then we take the next derivative, so for y double prime, we end up with minus a sine of t minus b cosine of t. And these all now have to get plugged into the equation the same way that we did with the last example. So this can be minus a sine of t minus b cosine of t minus 3a cosine of t plus 3b sine of t minus 4a sine of t minus 4b cosine of t. Before I put the right hand side in here, I'm going to combine this by sines and cosines. So I'm going to group this, I should say, by sines and cosines. So all of these are going to get grouped together, and we're going to have coefficients of, look at this, minus a minus 4a, so that's minus 5a plus 3b sine of t. And then same deal with the cosines. So we have, in this case, it's going to be minus 3a, right, minus 3a, then it's going to be minus 5b cosine of t. And all of this has to equal 2 times sine of t, right? And so we can write this as 2 times sine of t plus 0 cosines of t, right? We don't want any cosine of t on the right-hand side. And what this allows us to do then is to write down a system of equations. So this must equal this, right? There's one equation. And similarly, this must equal this. So there's two equations. These coefficients have to be equal. And what we end up with then is this. So we have our equation, negative 5a plus 3b equals 2. Negative 3a minus 5b equals 0. This can be written in a matrix equation. So I'm going to do it this way because I want to review Cramer's rule with us. But this can be written in a matrix equation now, where the coefficient matrix is minus 5, 3 in the first row, minus 3, minus 5 in the second row. The unknown constant vector, AB, goes here. And then the right-hand side, 2, 0, goes here. And so if we call this matrix here A, it's a little confusing because we have another A here. Let's call it something else. Let's call it M for matrix, right? Then Cramer's rule says that A is equal to the determinant of M1 over the determinant of M, and B is equal to the determinant of M2 over the determinant of M, where the M1 and M2 are obtained by replacing the first or second, respectively, column of M by the right-hand side vector. So this vector over here, 2, 0. So let's work it out, and then we'll see how this goes. Hopefully you guys remember this from an algebra course. But the determinant of M is just going to be this kind of diagonal product, right? So it's going to be 25 minus negative 9. So that's going to be 34 when you add those up, right? So that's the denominator. All right, and then we need to write down our other matrices. So M1, again, we get by replacing the first column with this vector, and the second column just stays the same, right? And so this means that the determinant of M1 is going to be negative 10 minus 0, which is negative 10, right? We do the same thing for M2. M2, we leave the first column alone, negative 5, negative 3. We replace the second column by the right-hand side vector, and then we compute the determinant. This one's going to be 0 minus a negative 6, so that's positive 6, right? 0 minus a negative 6, so positive 6. And so then this tells us, if we believe that this is called Cramer's rule. If we believe this then, right, then A, our coefficient A, is going to be negative 10 over 34, and our coefficient B is going to be 6 over 34. And this tells us exactly how to write down our solution, right? Because A and B are the coefficients of the sine and the cosine in our equation up here, right? So we can come back up here and we can write then that I'll write it right here. So that y of t is going to be negative 10 over 34 times sine of t plus 6 over 34 times cosine of t. So that is the non-homogeneous part of our solution. Just make sure we copied them right. Negative 10 over 34, 6 over 34. All right? The general solution itself is going to be the sum of these two, right? So the final general solution here is this function, negative 10/34 sine of t plus 6/34 cosine of t plus c1 e to the 4t plus c2 e to the minus t. Put a box around it. That's the solution. Okay? So that's how this works when there's trig functions on the right-hand side. All right. Let's look at a couple more examples now. This one I'm going to kind of leave as a bit of an exercise, but it's possible that we could combine these two ideas together, right? So we could write something like, let's stick with the same left-hand side, y double prime minus 3y prime minus 4y equals, and then on the right-hand side, let's say, okay, maybe the right-hand side is minus 8 e to the t cosine of 2t. All right, so this time we have an exponential. Our first example was an exponential function. Our second example was a trig function, right? But it's possible that we could put these together in this form, right? So the way that this works then is that our guess is going to be the following. So our guess is going to be that capital Y of t should be some linear combination of e to the t times cosine of 2t plus e to the t times sine of 2t. It's going to be the exact same reasoning that we use for the trig functions up above, that when you take the derivative, you're going to end up, it's going to be a product rule, but you're going to end up with sines and cosines, right, from taking these derivatives. So your guess needs to include both. So your guess in this scenario would be something like a e to the t cosine of 2t. You want to have 2t inside, so it's got to stay there, right? Plus b e to the t sine of 2t, and then you work it out. And again, if you change the order of this, you're just going to switch the roles of a and b. It's fine, right? You're going to determine them anyway. So I'm going to give you guys a few moments to do this one. I'm not going to actually do this one, but when you come back, I'll give you the answer to this one. All right, so I hope you guys figured this one out. This one, you go through this exact same process that we did in the last two. You're going to end up with a system of equations for these two unknowns, a and b. You can use Cramer's rule or you can use a different method. But in this case, what you should end up with is that a ends up being 10 over 13, and b ends up being 2 over 13. So the general solution of this one, remember, you have to include the homogeneous part, right? The homogeneous part is the same that we've had because we have the same left-hand side, right? It's the same as what we've been using. So it's c1 e to the 4t plus c2 e to the minus t. And our solution is then y of t is equal to non-homogeneous part. So in this case, that'll be 10 over 13 e to the t cosine of 2t plus b, so in this case 2 over 13 e to the t sine of 2t, and then plus the homogeneous part, so c1 e to the 4t plus c2 e to the minus t. All right, and so that's the solution of this one. Now we can put this all together actually and consider the following. So just for this one, let's just consider the following. Let's call this number 4 actually, why not? But let's suppose that we had a differential equation that had the same left-hand side. So we've been doing all this, right, with the same left-hand side, y double prime minus 3y prime minus 4y. And then on the right-hand side, we had each of the different right-hand sides added together from what we had before, right? So we could have our 2 e to the 2t, sorry, it was 3 e to the 2t, right? So 3 e to the 2t plus 2 sine of t, and then minus 8 e to the t cosine of 2t. And if we have this entire differential equation with this very complicated looking right-hand side, luckily it is complicated, but luckily the complication, right, is all added together. So we have these three different solutions in some sense, three different right-hand sides. What we can do is just add together all of our non-homogeneous parts, right? Because we have a linear differential equation, we have a linear right-hand side, we can handle those individually and add them back together after we've solved each one, right? So the general solution of this one is going to be y of t is going to equal, in some sense, y1 of t, which is our first answer, plus y2 of t, which was our answer to the second one, plus y3 of t, which is the answer you guys just worked out for the previous one, plus finally the homogeneous solution always has to be there, right? So y1, y2, y3, and then the homogeneous part. And so the total solution here is going to be that y equals, let's just go back up, it was negative 1/2, right? So negative 1/2 e to the 2t for y1, plus the second one was, just scroll up, but it was 10, negative 10 over 34. That was on sine though, right? Because I had these backwards from what we did on the next one. So negative 10 over 34 times sine of t. So minus 10/34 sine of t plus 6/34 cosine of t. Just make sure, but that was right, 6/34. And then plus this rest of the solution, right? So now we have plus 10 over 13 e to the t cosine of 2t, and plus 2 over 13 e to the t sine of 2t. And finally, the homogeneous part still has to be here, right? So c1 e to the 4t plus c2 e to the minus t. And that right there is the general solution of this differential equation with this complicated right-hand side. But remember how we did it, right? We solved individually. We found the solutions, right, for each term individually. And then we just added them together because everything here is linear, right? Everything is added linearly together. All right, and then of course, you know, I didn't highlight this, but homogeneous part, right, always has to get added on. So that's the basic idea there. Let's look at one more example, and then we'll state a theorem, and then this lecture, we can call it there. We do have an important example left to consider, though. So this example, what if we have, once again, the same left-hand side, so y double prime minus 3y prime minus 4y, but on the right-hand side, let's suppose now we have 2 e to the minus t. All right? So we might guess that we want to use a, right? Just based on everything we've done so far, we might guess that our capital Y should be something like a e to the minus t, right? But let's see what happens. So if this is our guess, then we need to take our derivatives, right? So y prime is going to be minus a e to the minus t, and y double prime is just going to be a e to the minus t. And when we plug all of this into our differential equation, we get y double prime minus 3y prime minus 4y ends up being a e to the minus t minus a negative, so plus 3 a e to the minus t, and then minus 4 a e to the minus t. And then if you add all these up, what happens? Well, you end up with 0, right? But the equation says that that should equal 2 e to the minus t. That can't happen, right? 0 cannot equal 2 times e to the minus t. It's impossible. We've lost, there's not even an a coefficient in here for us to determine, right? The undetermined coefficient is just gone. It's not even there. All right, so what happened? Well, look up here. E to the minus t is part of our homogeneous solution, right? So this right-hand side, this equation, really what I should be pointing at here is our guess, right? Our guess for the solution of the non-homogeneous part is actually a homogeneous solution to the differential equation. All right, that means it's always going to give you 0 when you plug in, no matter what the coefficient is. It's always going to give a 0 back, right? That's not what we have, so we need to now consider the right-hand side, right? So we want to get e to the minus t back. So what we do, it's very similar to when we studied the Wronskian. We know that a linearly independent function from this is t e to the minus t, right? So instead, what we do is we guess the following. So we guess that y is going to be equal to a, unknown constant still, times t e to the minus t. Essentially what I did was I took our guess and I multiplied by t. Okay, I multiplied by t. All right, so now let's check this. Let's see if this works. So y prime. Well, now when we take the derivative, we have to use a product rule, right? So now it's a e to the minus t minus a t e to the minus t. And then y double prime is going to be minus a e to the minus t minus a e to the minus t plus a t e to the minus t. Okay, obviously these combine, right? So this is now minus 2a e to the minus t plus a t e to the minus t. All right, now we plug in. Let's see what's going to happen here. So y double prime minus 3y prime minus 4y now equals negative 2a e to the minus t plus a times t e to the minus t. Then it's going to be minus 3a e to the minus t plus 3a t e to the minus t, and then minus 4a t e to the minus t. And look, at this time, what happens is the terms that have the t e to the minus t, those are the ones that end up canceling now. All right, those ones end up canceling out. So 1 plus 3 minus 4, that's 0, right? And the other two terms combine to give us minus 5a e to the minus t. That's good, because the right-hand side is supposed to be 2 e to the minus t, right? And so at this point, we see, okay, these cancel, and we can solve for a, right? So a has to be minus 2/5. All right? And so in this case, the non-homogeneous solution is going to be minus 2/5 times t e to the minus t. All right? And so our general solution is, of course, this function, negative 2/5 t e to the minus t plus c1 e to the 4t plus c2 e to the minus t itself. So we still have that homogeneous e to the minus t as part of our general solution here. Okay, so this gives us yet another idea. When we have this is a big reason why, and I alluded to this before, why we should solve the homogeneous equation first, right? Because otherwise we make a guess that's not going to be correct, right? We make a guess that's going to just give us a homogeneous answer, right? It's going to be 0. So if we solve for the homogeneous solution first, then we can compare the right-hand side that we need to the homogeneous solution, and we can determine our guess based on that. All right, and so there's a theorem for this, and we'll write it out. We're not going to prove it, but we kind of just worked out all the details for it. But here's the deal. So if we have a differential equation that looks like a y double prime plus by prime plus c times y, so linear constant coefficients on the left and g of t on the right, all right, then we're going to make the following guesses for g depending on the form of g. I'm going to make a table for us. So then make the following guesses for the form of our y, our non-homogeneous part, right, for y of t. So here's the table. I'm going to have a g of t over here, and then over here I'm going to write the form of our y of t, the guess. First case scenario here is that we have a polynomial on the right-hand side. We didn't work through polynomial, but you guys can check that this guess is going to make sense, all right? So I'm going to call this p sub n of t so that we can refer to it later. But p sub n is going to be a polynomial of degree n. All right, so this is going to start with a constant term, a0 plus a1t plus a2t squared, all the way up through a sub n t to the power n. So their polynomial is our guess here. All right, the y of t that we guess is going to be this. So the form of the y of t is going to be, in this case, a polynomial as well, right? So we would expect to get a polynomial as well. I'm also going to write here a t to the power s in front of this, and I'll tell you what this means in a little while. But this is going to be the adjustment for the case that we just talked about. So the homogeneous adjustment, we'll call it. All right, so in this case, what are we going to guess? We're going to guess unknown coefficient a0 plus a1t unknown a1, right, plus etc. We just continue with this. So a2t squared all the way up through a sub n t to the power n, where all these capital A's, those are the unknown coefficients that we're trying to solve for. All right, so that's exactly what we want to guess. Again, the t to the power s out in front, that's going to be the homogeneous adjustment. And I'll write down what that's going to be in a moment after we finish the other two cases. The next case is that we might have a polynomial just like this, so that's why I'm going to refer to this as p sub n of t, just as a polynomial, times an exponential function. So e to the alpha t. And in this case, our guess is going to be that polynomial that we guessed before times this, right? So times the exponential function. So the guess is going to be very similar. So t to the power s, a0 plus a1t all the way up to a sub n t to the n, this time times e to the alpha t. All right, and that's our guess. So very similar so far. Again, homogeneous adjustment out front. And then finally, the third case scenario is that we have a polynomial times one of the following. So I'll write it like this, and our text writes it this way as well. So polynomial times either sine of beta t or cosine of beta t. We're going to make the same guess regardless. And again, we've seen in our motivational examples that when you have a sine or a cosine, you need to guess a combination of both, right? And so in this case, our guess is going to be t to the power s times, big parentheses, polynomial, so basically it's this times sine plus this times cosine. So here's how we're going to write it. It's going to be a0 plus a1t plus, etc., a sub n t to the n, e to the alpha t sine of beta t, plus, and then b0 plus b1t plus, etc., all the way up through b sub n t to the n, e to the alpha t cosine of beta t. All right, so polynomial times the e to the alpha t, sine of t, beta t, etc. And then the whole thing multiplied by the homogeneous adjustment function here. All right, and so in this scenario where s is either 0, 1, or 2, depending on the homogeneous solutions. Right, so depending on the homogeneous solutions of the DE. So when I say that, what do I mean? I mean the solutions of ay double prime plus by prime plus cy equals 0. All right, so it's possible, as we know, that you could have, for example, if you just have your solutions could be e to the t and then t e to the t, and then your guess over here could be e to the t again, right? So then you need to guess e to the t plus e plus t e to the t times, right, t squared in this case, because they would both be, I think I said that completely wrong. But if your answer over here, if you had on the left-hand side, let's just do an example. All right, let's say the homogeneous solutions are so c1 e to the t and c2 t e to the t. So repeated root, right? R equal to 1 in this case, right? Repeated root. Then in this case, if your right-hand side, if g of t is equal to e to the t, then you must guess, right, that your capital Y is of the form e to the t doesn't work, t e to the t doesn't work, because that's homogeneous, so you need to guess t squared, e to the t. And there's your constant, unknown constant a, undetermined constant a right there. All right, so that's the idea. That's where the s comes in. So s is either 0, you don't need it at all, 1, you need to multiply by 1t out in front, or 2, t squared. All right, and so since we're sticking with second order equations here, t squared is the highest that you'll have to go, the highest in terms of powers of t that you'll have to go. All right, let's finish this off with just one more example. I want you guys to guess the form, based using that theorem, guess the form of the solution for the non-homogeneous part of the following equation. So here's the differential equation. Y double prime plus 2y prime plus 5y equals 3t e to the minus t cosine of 2t minus 2t e to the minus 2t cosine of t. I want you guys to write down a guess for the form of capital Y of t. Don't actually solve for the coefficients on this one, but just take a moment and write down the guess that you think using this theorem. Okay, so figure out which case it fits in, figure out exactly what you need to multiply by. But figure out the form, and I'll check back in with you after you've had a moment to work on it. All right, so now that you've had a chance to work on this, we can try together to work out the form of the guess of the non-homogeneous solution to this. So we always start though with the homogeneous part, just to make sure that we know what we're working with. So we're going to solve this equation first. This one has characteristic equation r squared plus 2r plus 5 equal to 0. This is, of course, so this is going to be what? R squared plus 2r plus 1 plus 4. So we can move this over, minus 4. And then this is r plus 1 quantity squared equals minus 4. So r is equal to minus 1 plus or minus 2i. And so this means that the homogeneous solutions, y sub h, so y sub h here, this solution is going to be c1 e to the minus t cosine of 2t, right? Plus c2 e to the minus t sine of 2t. This is going to help us make our guesses now, right? So the first one is homogeneous, and it's multiplied by homogeneous, right? So let's start by just making our guess just based on this one. So for y1, our guess for y1 here is going to be, this is a polynomial, 3t, times exponential times trig, right? So for this one, our guess has to be a1 times t plus a0, polynomial of degree 1, times e to the minus t times cosine of 2t plus b1 times t plus b0 e to the minus t cosine of 2t. Okay, but now we need to make sure, so e to the minus t cosine of 2t, e to the minus t cosine sine of 2t, these are both homogeneous solutions, right? I don't know if I said this right or not, but I wrote down cosine twice. One of these has to be sine, of course, right? Doesn't matter which one, but we'll change the second one. But this is homogeneous, right? So we need to multiply by t to make sure that none of the guesses are a homogeneous solution. Right now, the term that has a times t times this, that's okay, right? But the one that's just a0 and b0, that's not okay. So we need to multiply this one by 1t to the first power, right? 1t times the whole thing because of the homogeneous solution over here. Okay? Now the second one, these are reversed, so this is not a homogeneous solution. So for this one, we just have to write down our guess. It's going to be very similar, right? So y2, our guess is going to be polynomial of degree 1. So we've already got c, so I'm going to go to d now. So d1t plus d0, e to the minus 2t in this case times cosine of t, plus, and then we'll go to e, I guess. So e1 of t plus e0, polynomial of degree 1, e to the minus 2t sine of t. All right, and our guess is the sum of these two. So we add these together, right? So our total guess here of y of t is going to be that this should be t times a1t plus a0 e to the minus t cosine of 2t plus t times b1 of t, that's b1 times t plus b0 e to the minus t sine of 2t plus, this one is just d1 t plus d0 e to the minus 2t. We didn't have to multiply by t here because this is not one of the homogeneous solutions, cosine of t, and then finally e1 plus e1 of t plus e0 parentheses e to the minus 2t sine of t. Okay, and you can see why we don't want to really work this out and find the coefficients here. If you do decide to try to solve this and find the coefficients, you're going to probably want to treat the y1 and the y2 separately. Those are each going to give you systems of 4 equations and 4 unknowns. There's 4 unknown coefficients, undetermined coefficients in each of these two guesses, right? So altogether you'd have a system, an 8x8 system. It's much easier to solve the 4x4 and then the next 4x4 and put those together. All right, but we'll leave this here. That's how you make the guess. That's the most important thing here, is how to make your guess for the undetermined coefficients. And then from there, it's just very careful computation to find the values of those. So we'll leave this here, and I'll talk to you guys in the next lecture.